Hello everyone, welcome to the second unit of our course on techno-economic analysis in green engineering. In this unit, we will delve into the crucial concept of the time value of money. This principle is foundational in understanding how money's worth changes over time, affecting investment and the financial decisions in green technologies. We will start with the basics of cash flow diagram, explore interest and economic equivalence, and apply these concepts to the practical scenario involving feed-in tariff setting. The time value of money includes how payment, interest rate, and the periods influence monetary value over time, which is an essential consideration for decision-making in engineering. The cash flow diagram not only simplifies complex financial data, but also bridges the gap between the theoretical models and real-world applications. Such a diagram helps answer the critical questions such as whether to invest in greener projects, lease versus buy decision for more energy-efficient equipment, and consideration for replacing outdated technologies. Cash flow diagram is a straightforward visual representation showing the timing and the magnitude of cash flow associated with the investment. Basically, this is really nothing more complicated than a line. Let's take an example. A company is considering buying a machine which costs $20,000. After 7 years, the salvage value will be $2,000, and overhaul costing $5,000 will be needed in year 4. O&M cost will be $2,500 per year. And now, please draw the cash flow diagram associated with the purchase of this machine. So here you can see, we first draw the line, and then we next draw the down arrows which represent the money going out, such as the initial purchase of the machine and the midlife overhaul in this case. And then we draw the up arrows, which indicate money coming in, or savings. For instance here, the salvage value of $2,000 at the end of year 7. In practice, cash flows can occur at the beginning or in the midterm of an interest period or at any time point. To simplify, we always make assumption, which is to place all the cash flows or transactions at the end of an interest period. If you can do this, then you are one step toward being able to do the other problems that we'll do later in this course. Alright, let's think about this for the moment. If I offer you $100 now, or $100 a year from now, which would you choose? Most would prefer $100 right now, right? But why? This is where the concept of a time value of money comes into play. Money has a time value because, first, the earning opportunities. If you take $100 today, you can invest that money and earn more money over time. For example, with a 10% interest rate, your $100 could grow to $110 in just 1 year. The second is because the inflation impact. Money lost value over time due to the inflation. So $100 today will likely buy you more than $100 next year. Understanding it means you better prepare to make the smart financial choices. Let's break down how interest is calculated, focusing on 2 methods, the simple and the compound interest. It is essential for making smart decisions about the loans and investment. So let's start from the simple interest, which is straightforward. If you borrow or invest $1,000 at a 10% annual rate, simple interest at 10% of the principal each year, and after 3 years, you will earn $300 for interest, and which will sum up to $1,300 in total. The second is the compound interest. Here is where it gets interesting. Compound interest means you will earn interest on your interest. Let's start with $1,000 at a 10% rate. By the end of 3 years, you are looking at $1,331. That extra $31 comes from the interest earned on interest. Compound interest is remarked as the greatest mathematical discovery by Albert Einstein because it really captures the essence of how money can grow exponentially over time. And Benjamin Franklin beautifully summed it up. Money makes money, and the money like money makes money. This quote emphasized the power of compound interest. Each layer of interest you earn will increase your base, which in turn generates more interest. So when you invest, you are not just earning interest on your initial sum, but also on the interest earned in previous period, which will cause your wealth to grow faster than you might imagine. It is a reason why starting to save and invest early can have such profound long-term benefits. Next, let's dive into the concept of economic equivalence. Imagine you got a choice, $100 right now or $110 1 year from today. With an interest rate of 10%, these two options are essentially the same value to you financially. That is what we mean by economic equivalence. It doesn't matter if you choose the money now or later. Their value adjusted for interest is basically the same. Let's see how compound interest can be used to achieve economic equivalence. Imagine you invest a sum of money, let's call it the principal, often denoted as P. Over time, this amount grows due to the interest. And we use the specific formula shown in this slide to calculate the future value Fn of that money. Remember what we just said? Compound interest means your interest earn interest, which will create a snowball effect, and therefore this is called the compounding process. Now let's flip the concept. If you know you need a certain amount in the future, you can work backward to find out how much you have to invest today to reach that goal, using the same formula but in reverse. This is called discounting. It is like reverse engineering your financial planning. Whether you are saving for your education or retirement, understanding compound interest can give you the powerful perspective on savings and investing. Here's how this breaks down. For the future value formula, this is known as the single payment compound amount factors, or simply the growth factors. This factor shows how the principal amount will increase over n period at an interest rate of I. And for the present value formula, this is a single payment present worth factor, also known as the discounting factors. This helps us determine how much the future sum of money is worth in today's dollars, accounting for the same interest rate and the time period. So let's take the example. Imagine you have investing in green energy stock and $15 per share. If the stock price is expected to increase by 12% annually, you will naturally wonder how long it will take for your investment to double. To find it out, we use the formula shown here, where P is your initial investment, I is the annual interest rate, and N is the number of years. If we set F equal 2 times P, the equation becomes 2 equals 1.12 and the power of N. To solve an N, you will take the natural logarithm of both sides, so it will come out the 6 years approximately. And here I would like to introduce the rule of 72, which gives us a handy way to estimate this problem. You can just simply divide 72 by the annual growth rate. So, given a 12% increase, is 70% divided by 12, which equals 6 years. That means if the growth remains consistent, your initial investment could double in about 6 years. This simple calculation is a quick tool to assess investment potential, helping you make a smarter, more informed financial decisions. Let's now delve into the concept of equal payment series in financial calculations. This is where we encounter regular identical payments known as A, made over a series of periods, stretching from the first period up to the period N. For example, if you are making annual payment on a loan or receiving the regular annuity payments, understanding this series helps in calculating the total amount of money paid or received over time, adjusted for interest. P represents the present value of all payment made, and F represents their future value at the end of period N. Here, we are going to introduce 4 different financial conversion factors associated with the equal payment series. Let's start with the compound amount factor. This factor shows us how uniform payment A made at the end of each period accumulate over time to a future sum, which is F, given by the formula shown here. And we can see that when we sum it up, this series of payments is basically a geometric progression. The sum of a geometric sequence is given by the box shown here. And we can apply this to our cash flow scenario. Then we can simplify the future value formula using the compound amount factor formula. This equation efficiently captures the future worth of an annuity considering compounding effect, turning a series of equal cash flows into a single future sum. For the sinking fund factor, our focus shifts to finding out how much you need to set aside periodically, A, to accumulate a specified future sum. It is like reverse engineering our previous factors. Instead of calculating the future value of payment, we determine the periodic payment required to reach a future value. The third is the capital recovery factors, which help us understand how much needs to be paid annually to recover an initial investment P and cover the interest cost, such that by the end of period N, the investment is paid off completely. This is vital in loan repayments and amortizing cost of projects or investment over their useful life. Finally, the present worth factors is about determining the present value of a series of future payments. This factor is crucial for valuing long-term projects or cash flows. Comparing the present value of future consistent payment against a single lump sum value today. So we have reached a summary slide for this section on the time value of money. As we have just explored, understanding these financial factors and the formula is very important for evaluating investment and the financial decision in engineering economics. This table summarizes the key factors we have just covered, each with the formula and the corresponding Excel comment for practical application. The cash flow diagrams on the right visually represent how each factor operates over time.